On this informal talk on numerical in algebra, we're going to see how we solve ax equal b nowadays. So, in the first video, we have seen why to solve ax equal b is so important. Ax equal b, the fundamental problem of linear algebra. And we also have seen how's the typical A nowadays that comes in applications. A is usually sparse, okay? And we want to use its structure to make its calculations faster. So we want to solve ax equal b, and we're going to see how it's solved nowadays. And for sure, it's not solved by elimination. It's too expensive to the matrix that we have nowadays. Billions, dozens of billions of lines and columns, maybe trillions of lines and columns. So for matrices of this size, we would like to use the A structure because it's sparse. It has a lot of zeros. So if you use this information in the structure, for example, if A is symmetric or positive definite, symmetric and positive definite, we would like to use its structure to make more faster calculations. And we are particularly interested on multiplications from a matrix by a vector because it's cheap. Okay, so let me show you how we do nowadays. Initially, we're going to just by the first move, just to subtract ix from both sides. We had ax equal b, the thing we want to solve. You want to find x that solves ax equal b, and we just subtract ix from both sides. So we can do it, no problem. So I'm just rearranging elements. A minus I x equals b minus ix, no problem. Just rearranging elements. And I'm now just going to put this ix to this side and this to this side, and no problem. We still have ax equal b. Reading by another way, another form, okay? Ix equal I minus ax plus b. We are still solving ax equal b. So let me show you. We have here ax equal b, written in another form. I didn't tell you, but I, it's the identity matrix. In its main diagonal, we'll just have ones, and in another elements, we have just zeros. But I could tell you, well, I'm telling you right now. But we're going to see that it doesn't matter actually, because we are not going to use y. We're going to use p. So let's just modify y for p. So I'm still solving ax equal b, but now I have px is equal p minus ax plus b. It's still solving ax equal b. Well, now is the most important slide of this presentation. We want to solve ax equal b, but we don't want to solve by one shot. We want to solve in an iterative way. What is this? Well, I have a guess for x, for example, in the first shot, x0, and then I want to find another x, the following x, that is closer to the x that I solve for ax equal b. So, by the first place, let me just calculate the right-hand side for some x, for example, x0. Suppose x0 is the zero vector. Okay, I know p. It's a matrix that I know, that I choose, like I, the identity matrix. So I have p, I have a. That's this matrix of my problem. Let me just subtract those matrices, p minus a, and I have a x0, xk equals 0. That's 0, the zero vector, and I have b. So I have a first choice for my right hand side, and from this first choice, I can choose the next xk plus 1. That is the next choice for x. So I'm just starting with a general x0, that I suppose it's close to x somehow. But I really know, I I will really know that x1 and x2 are closer to dx from ax equal b than x1 x0, for example. So we just calculate the right hand side, and then we calculate the left hand side, x1. So example, we have x0. We start with an x0 vector, for example, and I calculate the right hand side. What do I have? The left hand side, p x1. So I got x1, and I hope x1 is closer to x than x0. I have x1, and then I calculate p minus a x1 plus b. And what do I get? x2, and I multiply by p. So when can I stop this? Because I need to stop sometime. I need to get something that's close to x when the error is as small as you want or as I want. So show me. So let us just subtract these two equations, these two here, px1, this equation, and this equation. Let us just subtract these equations. Okay, px2 minus x1, p minus a, x1 minus x0. But what is x1 minus x0? It's an error, right? It's an error vector. I'm just taking the difference between two estimatives. It's an error on the variable I want to find. So I have an error here. And I also have error 2, e2, another vector, x2 minus x1. So let me just rewrite this equation. p e2 is equal to p minus a e1. Let me now just multiply both sides by p minus 1. Actually, I'm not going to do this on my calculations. It's just to show algebraically what's happening. Well, let us see. P minus 1 times p is the identity matrix. I can just rearrange and do not write I e2. It's just e2. And p minus 1, when I multiply by p, is also the identity I. And p minus 1 times a, well, it's p minus 1 times a. I'm just put here e1 on multiplying both matrices. Well, I could do this forever for e3, for e4. But let me now show you what happens on e3. Let me show you that e3 depends on e2 and e2 depends on e1. So let me rewrite this term e2 like what it is, I minus p minus 1a times e1. So can you see, I'm sure you can see, that this term is now put here twice. So that is what you get right now. E3 is this term, this matrix. It's a matrix, square times e1. Can you imagine what's gonna happen to e4? The same. I minus p minus 1a to the power of 3 e1. Well, we can see that the error, the thing, the variable we are interested in, we want that error is as small as possible. So an error in the step k plus 1 is equal to this matrix that I'm going to call M, the identity, minus p inverse times a to the power of k, the step k, e1. And matrix M will gonna tell us everything about conversions. Will it happen? How fast? Because if you know about eigenvalue decomposition, singular value decomposition, you know that eigenvalues of this matrix M will gonna tell you everything about conversions. Particularly if we have eigenvalues in a range, particularly minus 1 and 1, in absolute value less than 1, then we have a very interesting situation, and our error will going to converge to 0. Okay, but we usually do it. We usually stop. We usually stop sometime much before this, because we may have interested in an error that is not that close. Well, it will depend on the application and what are you doing. So this is usually what happens when we solve AX equal B nowadays. The matrix P we call preconditioner. It's approximation of A. So as close as P from A, and with some ideal properties, we are going to solve AX equal B very fast. And for sure, the X that we find for iterative methods will come closer to dx from AX equal B by iterative methods. And we call this process I've shown here by a simple way by pure stationary iterative method. It's iterative because, well, we solve step by step, trying to get close for dx from AX equal B. And it's pure stationary because we are just doing the same stuff every time. Let me show you here again. We are always multiplying by the same matrix. We're going to see that multigrid and Krylov subspace methods, the state of the arts in methods to solve AX equal B nowadays, we're going to perform better than pure stationary iterative methods because they're more intelligent. They're going to use more information to solve AX equal B. So I hope you have enjoyed these videos, and please, if you have doubts, just leave a comment. Thanks.